17.5 Decision making under 17.5 Decision making using decision trees. In the previous section, we demonstrated the decision making under this technique using decision tables. In this section, we will show you how the same technique can be applied using a decision tree. Decision trees have two main components, squares, which are used to denote alternative, and circle, which denotes the state of nature. Let's return to the Gimbel department store example to see how decision trees can be used. Figure 17.1 displays the information that was provided in the previous section. The red box on Figure 17.1 shows Christine's alternative: to place a small, medium, or large order. Once her choice is made, demand will be strong 60% probability or weak 40% of probability. The state of nature are shown with the green circle. The probabilities for each state of nature and the corresponding payoff are also displayed in the decision tree. Once our decision tree is constructed, we are now ready to evaluate the alternative, which are shown in Figure 17.2. As you can see in Figure 17.2, we've numbered the three states of nature arbitrarily to help with the upcoming calculation. We start by calculating the expected monetary value, or EMV, for each state of nature on the right side of the tree. Large is equal to 80,000, medium equal to 55,000, and small equal to $48,000. If this seems like deja vu, it's because we performed this same calculation in the previous section when we were using decision table. Notice that each expected monetary value, or EMV, is displayed over the corresponding state of nature. As we continue to move to the left of our tree, we come to the red box indicating Christine's tree alternative. She likes the $80,000 profit the most, so we prune the branches for the medium and small order with double line, which indicate those alternatives are eliminated. The finishing touch is to display the 80,000 profit over the red box. Using decision trees to make sequential decision. At this point, you may be wondering what benefit a decision tree provides, because it duplicates the result you get when using decision tables. There are many examples in the business world that involve sequential decision. That is, the decision maker selects a choice, and after the ensuing state of nature occurs, he or she is faced with another set of alternatives to choose from. This is where decision trees come in handy. For example, suppose Christine can hire a firm to conduct a market research survey at the cost of $10,000. The survey will provide additional information about the demand for Nicole Miller dresses during the fall season. Christine can use a decision tree to choose one of the following options. If the benefit of the survey do exceeds the $10,000 cost, Christine should conduct the survey and use this additional information to decide on the size of the order. If the benefit of the survey do not exceed the $10,000 cost, Christine should decline the offer to conduct the survey and use current information to decide on the size of the order. Figure 17.3 shows the first set of alternatives that Christine is faced with in the decision tree, whether or not to conduct the survey. Figure 17.4 shows the state of nature that will occur if a survey is conducted. Figure 17.4 shows that if the market survey is conducted, one of two states of nature will occur. The survey will predict that the demand for Nicole Miller dresses will be either strong or weak. Let's define this event as follows. SSR is the survey result predict strong demand. WSR, survey result predict weak demand. Because decision trees rely on decision making under race, we need to assign probabilities for each state of nature. As you can see in figure 17.4, Christine assigned a 50% probability, which the survey will show that the demand for the dresses will be strong, and a 50% probability, which the survey will show the demand will be weak. These probabilities can be expressed as follows. P of SSR equal to 50%, P of WSR equal to 50%. In the next section, we will show you how to calculate P of SSR and P of WSR. In the meantime, let's just assume these values are given to us. Figure 17.5 shows the next section of the decision tree if the market survey is conducted. Assume for a moment that the survey predicts strong demand. As we can see from the red box in the top branch of this figure, Christine will then be faced with the decision to place a large, medium, or small order for the dresses. Notice in figure 17.5 that after Christine decides on an order size, one of the two possibility states of nature will occur. For this example, we will assume there is an 84% probability that the demand for dresses will be strong and 16% probability that demand will be weak. I will demonstrate how these probabilities are determined in the following section. We expect the probability of strong demand to be much higher than weak demand here because this portion of the decision tree assumes our market survey predicts that demand will be strong. Otherwise, we need to fire our marketing research firm. That is, given that a strong survey response has occurred, there is an 84% probability of experiencing a strong demand and a 16% probability of experiencing a weak demand. Let's define the following event. SD is the strong demand for dresses occur. WD, weak demand for dresses occurs. The previous paragraph has defined the following conditional probabilities which were shown in figure 17.5. Probability of SD given SSR is equal to 84% and probability of WD given SSR is 16%. These two conditional probabilities are also known as posterior probabilities because they are based on the additional information from the market survey predicting strong demand. Also note that the payoff for each combination of order size and market demand are shown in figure 17.5. These are the same payoff at the beginning of this example. What happens if the market survey is conducted and it predicts weak demand for dresses? Figure 17.6 updates our decision tree and includes this scenario. If the survey predicts a weak demand, Christine still has to choose among the same three order sizes and is then faced with the same two states of nature and corresponding payoffs. The only difference in this section of the tree is that because the survey is predicting weak demand, the probability of weak demand, 64%, exceeds that of strong demand, or 36% in figure 17.6. So probability of SD given WSR is 36% and probability of WD given WSR is 64%. Again, for the time being, we are assuming these posterior probabilities are given but will be calculated later. Recall that Christine does not have to spend $10,000 to conduct the survey. This section of the decision tree is added in figure 17.7. This part of the decision tree should look familiar. We constructed it back in figure 17.1. Notice that the probabilities for demand revert back to the original values. P of SD equal to 60% and P of WD equal to 40%. These are known as prior probabilities because Christine does not have the luxury of relying additional information from the survey. As you will see in the next section, these prior probabilities can be revised with additional information to produce posterior probabilities. Figure 17.7 displays our fully constructed decision tree for Christine. We are now ready to evaluate this tree to decide what Christine should do. Let's start by determining the most profitable alternative if the market survey predicts strong demand. In figure 17.8, I've arbitrarily numbered each state of nature to highlight this calculation. We start by calculating the expected monetary value, or EMV, for each state of nature associated with a survey that predicts strong demand. Green circle 2, 3, and 4. These results are highlighted in orange in figure 17.8. Large equal to $152,000, medium equal to $97,000, and small equal to $55,000 to 100. For this scenario, Christine chooses to place a large order of dresses or the large EMV, which is indicated in the decision tree by pruning the medium and small branches. Figure 17.9 highlights the EMV calculation for each state of nature associated with a survey that predicts weak demand. green circle 5, 6, and 7. Large equal to 8,000, medium equal to 13,000, and small equal to $40,800. Because the survey predicts weak demand will occur, Christine chooses to place a small order of dresses, which is indicated in the decision tree by pruning the large and medium branches. We can now calculate EMV1 in figure 17.9, which represents the expected payoff for conducting a market survey, or green circle 1. This value is known as the expected value with sample information, or EVWSI. Here, we have a 50% chance of an expected profit of $152,000 if the survey predicts strong demand, and a 50% chance of an expected profit of $40,800 if the survey predicts weak demand. Conduct survey equal to EMV1 equal to EVWSI equal to $152,000 times 50% plus $40,800 times 50% equal to $96,400. Recall from the previous section that the expected monetary value represents the long-term average payoff. In other words, if Christine conducts the survey over many fall seasons, we expect the payoff to be $152,000, roughly half of the season. Survey predicts a strong demand and $40,800 for the other half of the season. Survey predicts a weak demand, resulting in an average payoff of $90,400. The last evaluation step is to determine the expected payoff if Christine decides not to conduct the survey. Figure 17.10 highlights this EMV calculation. Green circle 8, 9, and 10. This scenario refers to the original decision tree shown earlier in figure 17.2. Large equal to $80,000, medium equal to $55,000, small equal to $48,000. Without conducting a market survey, Christine chooses to place a large order of dresses, which is indicated in the decision tree by pruning the medium and small branches. The expected payoff of $80,000 is known as the expected value without sample information, EVWOSI, because it is determined without the luxury of having market survey information. We are now ready to make the decision to conduct or not to conduct the market survey. If we conduct the survey, the expected payoff is $90,400. However, we need to subtract the $10,000 cost of the survey, which results in a net expected payoff of $86,400. Because $86,400 is greater than $80,000 expected payoff of not conducting the survey, Christine should conduct the survey. Figure 17.10 indicates this decision by pruning the no survey branch. If the survey predicts strong demand, Christine should place a large order of dresses. If the survey predicts weak demand, Christine should place a small order of dresses. Last question for this section, what is the most Christine should be willing to pay for the market survey? What I'm asking for here is known as the expected value of sample information, or EVSI, which can be found using equation 17.4, where EVSI is the expected value of sample information, EVWSI is the expected value with sample information, EVWOSI is the expected value without sample information. Using equation 17.4, the expected value of sample information is EVSI equal to EVWSI minus EVWOSI equal to 90,400 minus 80,000 equal to $16,400. In other words, Christine should conduct the market survey as long as it costs less than $16,400. Thank you.